And so just to highlight a couple of different areas within these EV battery modules where adhesives are used and how we are able to use our adhesives to help improve consumer safety. There's two main areas on the module level, again, where adhesives are used. The first I haven't mentioned yet, and it's actually an adhesive that has one function only. When you're actually designing and building the modules from individual cells, an acrylic adhesive, so usually a relatively inexpensive material, is used to help align the battery cells with each other before the system is placed under pressure, which these systems are always under some amount of pressure. So they're used for this one application, but then they sit ambiently between the cells for the remainder of the battery's life and really don't have a function following that. But this is actually an area where we saw an opportunity, and I'll talk a little bit more how we're working towards developing an adhesive that provides both this alignment function, but also provides some passive protection from the thermal events that can occur in these systems. And then, as I mentioned previously, thermal interface materials. These are high conductivity systems that are placed between the battery cells themselves that allow for wicking of heat during normal operation. So these thermal interface materials or potting compounds have very high filler levels. We're talking 60 or 70% by solids percentage, which allows for what's called a percolation network or easy transmission of heat between the two surfaces due to the high level of fillers that are in these potting compounds. And so these thermal interface materials really do well at allowing for passive heat dissipation during normal operation, but they can have some problematic effects during thermal runaway events due to this high thermal conductivity. And so to look at the difference between these thermal interface materials and some of the materials we've been developing for thermal runaway protection, we turned to C-Therm and in particular the Trident TPS system to try to help us understand how varying the filler level and the adhesive thickness can change both thermal conductivity and the ultimate performance in thermal runaway protection that these adhesives can provide. As was mentioned by Aria earlier, this can be difficult when looking at thin film adhesives. And at the beginning of this particular project, we did exactly what he talked about. We were layering up adhesives constantly to get very thick films so we could measure them, which, while it worked on the short term, was relatively impractical for rapid development of materials, and also induced a lot of unnecessary interfacial effects that we, in the long term, determined were providing negative value to us. And so, in conjunction with the C-Therm team, we looked more about how we could look with our materials and test natively made thin film materials and see how consistently we could get measurements on them in terms of the thermal conductivity. These direct measurements give us a twofold advantage. They allow us to rapidly iterate, so materials can be made and tested almost immediately without having to take the time to stack materials. But it also really gives us confidence that we're not inducing interfacial effects, which can really be detrimental to our long-term goals. And so on the right, I'm showing a graph here with two different versions of the thermal runaway protection adhesive that I'll talk about here in a moment. But you can see that at both 75 microns and 150 microns, using the TPS system, we can get very similar thermal conductivities. This is then the intrinsic thermal conductivity of this material. It allows us to have confidence that we can measure these systems and iterate rapidly to help improve product development.